Okay, great. Well, welcome everyone to another installment of Astronomical Observations and Technologies Instrumentation. This is the first presentation of the final projects for the class. So please welcome from the Rochester Institute of Technology, Muyun Liu.
Hello everyone, I'm Muyun Liu, and today I want to introduce my final project on X-ray spectrum fading of the nearest black hole candidate. So today I will first introduce the object I'm working on, and then introduce the spectrum fading approach that I use, and the observation data of the object, and then show you the results and the spectrum I got, and compare my results with some previous work on the same object. So my initial scientific question is that what are the properties of the nearest black hole? So for people not very familiar with black holes and this subject, we first need to answer three more fundamental questions. So what are the properties of the black hole? And how do we find a black hole? Since black hole is a theoretical model that an object is so massive that light can't escape from it. So theoretically, we can't observe a black hole. And which black hole is the nearest one that I'm going to work on? So first, no-hair theorem. This tells us that when an object has become a black hole, only three properties are observable outside from it. It is mass, spin, and charge. And usually in observational research of a black hole, charge is really considered unimportant, and usually we assume it to be neutral and we don't consider it anymore. And spin is defined by a dimensionless spin parameter, and so it is normalized when this parameter equals to 1, it means the maximum spin allowed by relativity, and it could be negative or positive. When it is positive, it means it's prograde. It means the matter around it orbits as the same direction as the black hole itself. So when it is negative, it is retrograde. And so the second question is how we observe a black hole. So observationally, when a black hole has a companion star, and the companion star is really much more larger than the black hole itself, because black hole is so compact, and so that the black hole can draw material from the companion star, and thus in this process, the lost matter of the companion star forms a disk-shaped structure around the black hole, and this is the blue area in this picture. And then here are jets, and they're appearing very high energetic objects, but I don't think that's the structure that the object I'm studying on have. My object doesn't have a jet. So the viscosity of the matter works as a frictional force, so that it will result in dissipation of heat. That is to say, the radiation. That's why we observe the black hole, and the matter in the accretion disk drifts gradually inwards until it reaches the innermost stable circular orbit, and that is our isco. And if it moves beyond this point, it will irretrievably be absorbed by the black hole. So in this picture, and usually upper limit of the luminosity called Eddington luminosity, which is defined in a way that if the luminosity exceeds this value, the photon pressure will be larger than the inward pressure caused by gravity. That is to say, the bottle will lose matter gradually. So the first question is which black hole I'm looking at. So for now, people have observed 21 black hole boundaries in total, and the one we're looking at is here. And it is relatively small. So in this picture, a accretion disk is at this, and this is the connected star. So according to some formal papers, this one, these are some data of the A0620, the nearest black hole candidate. So how near it is 3,000 light years away from us. And according to this paper, the mass is 6.6 plus or minus 0.25 solar mass. And this paper actually only calculated the spin, and this group has done some work to constrain the mass, and it is in another paper. And in this paper, they just used the result they got from their previous work, and it is X-ray transient, which means that it was very luminous for a time, but now it is quiescent. That is to say, it has very little X-ray radiation now, but it was very, very bright in X-ray band when it was in 1975 to 1976, and with a peak of 50 Craft. For reference, it is more luminous than any other X-ray objects. The sum of the X-ray that they emit, it's more than that sum of. Get it? Okay. So the second part is the spectrum fitting approach. So what do we mean by spectrum fitting, and why are we doing that? So this is a model of continuum spectrum of the accretion disk. As I just said, the accretion disk can be regarded as a multi-temperature black body, and its radiation can be reflected by the nearby cloud. And the nearby cloud is excited and get fluorescence, and it reflects back light to the accretion disk, and so that the spectrum we observed is composed of the intrinsic thermal component and the reflective component. And the reflective component is probably a power law component. And if we want to get the intrinsic spectrum mathematically, we need to invert this integration, because what we observe is the C is the count of photons in each energy, and the intrinsic is there, but it is integrated over the effective area, the redistribution, and times the exposure time. But mathematically it is not possible, because the crosstalk between the different energies, that is to say, the redistribution matrix is usually not invertible. And that's why we're doing the spectrum fitting. So this is called a forward folding approach. So let's assume a model with some defined parameters, and define a set of parameter values, and then convoke the model with the instrument response. As you can see, the RHE is the 1975, the X-ray telescope that was observing it was OSO 8, and it was the primary objective was to observe the sun, but it discovered something else very interesting. And it was launched in 1975 and ceased operation in 1978. So as you can see, the structure up there, I think it's a solar panel, and down here it's a wheel with 4 instruments, and it just rotates very fastly and to observe the different areas of the sky. And observing the 80620 is the data is from the C detector. As I mentioned, there are 4 instruments in that wheel structure, and C detector is one of them, and it has a wavelength of 2 to 60 kV, and the observation lasted for 3 days, in which the intensity of the source was 11 crab, and yep. So then I talk about the spectrum extracted from the website. So NASA has archival data of this OSO 8 mission, and we need some special tools to get the data and process the data. And so the first tool needed is called F-Tools, and so first run the script OSO FunFast and determine the good observing days, and then run the OSO TJ, I don't know, to download the appropriate raw data, and this procedure will give back the light curve and a 1 to 63 panel, the raw spectrum, and then use OSO FunFast again to determine a position for a good background region, and then use OSO PJ this command to get the background spectrum. And I was very lucky because on the website of OSO 8 there was examples of dealing with its data, and the example was exactly on 80620. So and spectrum I got was like this, and this is the count, because the data you got is it's count instead of intensity. Well, spectrum we always have intensity versus wavelength or energy, but this is the raw data, so it is rate over each channel. So there are 63 channels in total, and that is the background spectrum. Then I'm going to show you the fitting results. So article on the NASA website, and it just ignores it, so I guess it's not a very good data point. So then I set the plot, set the axis to be, the units to be energy, and then model it with a model, fit it with a model, and you press fit, and then it will ask you to give the initial value for each parameter, and you give it the parameters and tell it which is frozen, which is not, and it will give you the optimal results around this region. So this is the first plot I've got. This is the second. I just changed the initial value of the parameter, some of the parameters. And this is the third one, and I think it is probably the best one I can get for now. And then I draw a confidence contour with X-spec, and I think this is a deformation versus spin. So the fitting results are here. So you can read that. The model I used is that the first one I don't PH yes, it is a model in abstract in its package, and the package contains a lot of maybe hundreds of models, and this is a very basic model for the absorption of the interstellar medium, and it times the second one. The second one is a model that theoretically calculates the power law redistribution, and the third one is a model contributed by Dr. Gambi, and he's very interested in the deformation parameter and the spin parameter, something like that. He's a theoretist, I know, but the model has five think that's, so there's probably something wrong with the model or what I was doing, but I'm not sure. Obviously, I think that the spectrum I got is pretty much the same that I've seen from the OSO website with the example. And the only parameters that have the same fixed value that is say frozen is an H. That is the column density of the hydrogen molecule. And it was the only parameter of the first model, the absorption model. And I think I have very different value for the second one and the third one, the parameters. And so what about the research of other wavelengths? So I came across a paper that using optical and infrared photometry to study that object, and they've only calculated the mass. So, but it is very different from the paper that I referenced and the work the group has done before. Well, if you could recall from the former parts of this slide, that their value was like around 6. So I think using different data you can get very different results. And obviously you couldn't measure a spin with optical and infrared. And I think that's all.
Okay, we have quite a bit of time for questions, and I'm sure you were busy jotting down all your questions during the talk. So who wants to start?
So you have a binary system with a star and a accretion disk, right?
The binary system is
The
the
black-
black hole and the companion star.
Yes, and then the star is falling into the accretion disk, or losing material to the
Yes,
accretion
it
disk.
is losing material in the accretion disk.
On what time scale does the star lose all its material to the accretion disk?
So I think it's mainly due to the mass of the companion star.
Okay.
And as you can recall,
So am I correct, your question is, how long will it take for the star to disappear?
Yeah,
Because
yeah,
it's lost all of its matter to the
She addressed like
accretion
the
disk.
Eddington
Yeah.
accretion rate.
Sure,
That's
so-
from accretion disk to black hole. What's star to accretion disk time?
So do you know that, how long it would take for the star to dissipate due to mass loss?
I think it differs a lot from the size of the companion star. I think I came across some paper that the 21 batteries, 4 of them are, I forgot the word. Well, they're still emitting the X-ray, but 17 of them are transient. And so I think it's a relatively short period. Well, I think the offers was 1 year, so I suppose it is probably some time scale like that for a small one. Yeah, but for a large one, I'm not sure.
Well, do you know what the mass infall rate is for this system? How much matter is falling into the black hole per second or per year?
I think it's the accretion rate, right?
Yeah, so what is the accretion rate for this system?
I think it's here. I set 1.6 frozen.
1.6? 1.6 frozens? What is?
How many frozen is just I set it.
What units? What units? 1.6.
Per something year, billion years.
Per year.
Second.
Is there a reason that you set it to that?
Oh, yes, because I was referencing the previous
Okay.
work and
Okay. That's fair.
It's a good question though, because if you set your models with inputs according to previous research, you might end up reproducing previous research and not learning that it's wrong. Although in this case, I don't know enough about it to know. Were there other questions?
I have a question about, so we always say that people ignore a charge, but why?
I don't know.
I took E&M, I liked it. Why do we ignore charge so much? Are the effects just negligible, or are they just not common, or?
I think usually you just study the motion of the matter around it, but it's dominated by gravity instead of electron.
Do you know what the effects we can see that could be in
No, I really don't know about it. The black hole is charged.
Right. Are they even real? Is that the thing? Serious. I don't know.
Can you go back to the Eddington luminosity slide? Can you just expand more on what you mean of a geometrically thin and optically thick?
Geometrically thin means that the actual shape is really thin. Let's see. It means it is thin, just it's thin. And optically thick means that
You just can't see through it?
probably it means that the photon will encounter several collisions to go through that material. That's what optically thick means, I think. Because this is, I think it's plasma in the accretion disk, and it is very dense. So if a photon needs to go across that, it will just collide with particles, electrons. Means I don't know plasma, but anyway, it just collides a lot before it came across it. So I think.
I mean, is that just
I
something that
agree.
you assume in that formula? I don't remember. I know we talked about this before.
What?
Like, is that just something that you assume when you're looking at the Eddington luminosity? I guess should have been my question.
I think so.
Does the orientation of the accretion disk have to do with the properties of the black hole, like the spin? Like does it align with the spin?
I think the only thing I can say for sure is that the spin affects the R is code very a faster spinning black hole will have a much smaller R is code. That's all I have to say for sure. And obviously it just affects the shape of the accretion disk.
So the fitting program you did for the spectra, you were getting some parameter A out of it when you were done.
Parameter A.
Yeah. What was that
Same.
telling us about that? Like what, I guess I'm wondering if you got a different value for that, what is that saying in changes in our system for the black hole? So he got A equals 0.12 in the paper you looked at,
That's where it tested.
and you got something pretty close to his. What is
But
it?
it's very large.
Yeah, that's fine. I was just wondering, when we change the parameter A, say you got a different value like 0.6, what does that change about our spectra? What does it mean was different between, I guess I'm asking what A stands for. What
It
does it
stands
actually?
for spin, and in the how the spin affects the spectrum is something in the model which I don't quite understand, but
Okay.
I had a couple questions, and then we can go back if you have more questions. One relating to what Meg was asking about the Eddington luminosity. So it looks like you had an equation, and could you go back to that slide actually? That would help. So there's this Eddington luminosity, and I guess it says the Eddington luminosity has to be less than or equal to some expression, which you then express in units of solar masses. So for the sun, the Eddington luminosity is 10 to the 38, and the luminosity of the sun is 410 to the 33. So the Eddington luminosity is, what is that, 2.5, 10 to the 5, is that what it is, or is it 10 to the 4? 10 to the 5. So the Eddington luminosity for the sun is much higher than the luminosity of the sun. So the sun has sub-Eddington luminosity.
Has what?
Sub.
Yes.
Eddington. The sun is sub-Eddington, is the way it's phrased. And so if you consider an object that for some reason emits photons, and there's this concept of Eddington luminosity, that if the luminosity can't exceed the Eddington value, I guess is what the equation says. So why can't it exceed the Eddington value?
Because the radiation the radiation pressure exceeds the gravity, so.
Okay, so the pressure due to radiation exceeds the force of gravity, the pressure due to gravity, right?
Mm-hmm.
And if the luminosity exceeds Eddington, and therefore the radiation pressure exceeds the pressure due to gravity, what happens?
Well, it lose matter or
It pushes matter.
Yeah.
So somehow the photons are interacting with matter. There needs to be a way for the photon to interact with matter to push it.
Mhm.
So how does the photon push matter?
I'm not sure.
Does anyone know, how does the photon push matter?
Does it just thermally, I mean, photons are just energy, could it just thermally excite the gas? And I would assume
It could be thermal pressure. The photon energy is absorbed by the gas, and the gas attains a Maxwell-Boltzmann distribution characterized by a certain temperature, which creates thermal pressure. And that balances gravity and creates hydrostatic equilibrium, typically in a star. But that's not what this is. This is radiation pressure. So it's a photon directly converting its momentum to gas, pushing on it. Do you know what this is?
The cross-section,
Cross section of what?
a gas electron.
Electron. It's an electron cross section. Cross section for what physical process?
Scattering?
Yeah, so it's Thomson scattering. So this is the Thomson scattering cross section. So an electron interacts with the photon and can be pushed by the photon. If electrons aren't present, then the luminosity can't exceed Eddington. If there's no way to couple the radiation to the gas, then the radiation can just freely flow from the object. It won't push the object out. It won't make the mass loss. So this is derived by equating the inward pressure of gravity to the outward radiation pressure due to Thomson scattering of electrons. And it's more important on electrons because electrons are light. I shouldn't use the word light. They have less mass than a proton. So if there's an electron and a proton, then the momentum from the photon will translate into the electron more than the proton. But there is some drag because the electron pulls the proton in order to ensure charge neutrality. Otherwise, there'd be a big charge difference built up. There'd be lightning, I guess. But that doesn't happen. The protons are pulled by the electrons. So that's where that comes from. I think after all that, I think I have a question related to that. So those were really my questions. Oh no, that was it. Go to slide 11. Okay, what in the world is this picture? What is this picture? I take it that's a black hole.
Yes.
This is not a bagel. This is a
This is the accretion disk.
Accretion disk. And I think I know what this is, but you could just tell me?
Yes, in innermost stable circular orbit.
Innermost stable circular orbit, right?
Yes. And it is usually considered the inner range of the accretion disk.
I know people sometimes look for the last chirp to infer the mass of the black hole, and that's been done with the galactic center black hole. And then what's this? It looks like there's a yellow cloud above the bagel. What is that? Dish weird?
The gas cloud surrounded.
Yeah, what is that?
The gas cloud.
Why is there a gas cloud? There's a disk. I know what that is. I think matter falls onto the black hole or in the surrounding of the black hole and has angular momentum, which has a flattening effect that makes a disk, which we see in many different systems. But what's that?
I think it is just hydrogen molecule cloud, gas cloud, something like that. Because it just it reflects the radiation from the accretion disk and gives another component, another half of the spectrum, and contributes to the reflective.
So when an observer sees light from this system, none of this is resolved, of course. It's just an all-in-one pixel or something.
Yes, yes.
And it's the
spectrum.
combined light that you
Yes,
get.
the
And
combination of the intrinsic thermal and the reflective.
this reflected light, does it have, how do we know it exists? Is it because there's a second temperature, that there are two temperatures?
Yes, yes.
And so people infer from the presence of two temperatures that perhaps there's a H1 cloud.
It's just a very commonly used model for the continuum spectrum. You just suggest that there is a cloud very near to it. I think
A
that's.
lot of commonly used components of models are wrong. But I'm not saying this one is. But when people just repeat what other people have done for however many years, you know, it's interesting to question that. But again, I'm not saying in this case to question it because this isn't my field. Go to 19. So I see it's always good when you show plots to immediately describe the quantities that are plotted in the axes. It sounds like it's very pedantic to do that, but it actually helps a lot. So it looks like the y-axis is units of counts per second.
Yes.
This must have something to do with energy, or is it time?
Yes, it is channel. Each channel.
What does the channel correspond to, time or energy?
Energy.
So this is energy, so it would be good to have an axis time.
Oh,
This is on the source.
yeah. Yes, this is.
This is the background. So is this a nearby location on the sky?
Yeah, I'm also very confused about that because in the example and the paper, the background spectrum was taken at a different time slot than its source. So I just follow that, and I think they are not very near. And according to the paper, it mentioned that the background, the region that you take the background is not very important for the source.
Well, it looks like the source is a lot brighter than the background.
Yes, I think that's right. Yes, that's right.
You know, the fact that the background has a shape that looks like the source tells me there's contamination. Because I don't know that blank sky should have a spectrum like that. I would have expected blank sky to be noise. So, but, you know, it looks like it's tiny,
Yeah.
right? 0.6. So it doesn't matter at all. Okay. And by the way, when I'm asking these questions, think about your own presentations. Right? The final question is, and you all should have this, is where is your slide giving the answers to your questions?
Oh, I see.
What you could do is just go back to the slide with the questions and then just tell us what the answers are. Is that the third slide or?
Deserve that. Yes. The question is what
Okay, but that's not something you measured in your study.
Yes, and the only thing I measured is spin.
Okay. And, so, you know, like I've said before, it's not as if the only way science happens is where you ask a question and then you answer it exactly. But if you were to go backwards in time, you might have had a question, the question you posed might have been, what is the spin of this object, right? So go back to the other questions.
The questions, right?
Yeah, how do you find a black hole? So is that something you figured out?
No, I just said, to answer this question, we must know the
Okay.
fundamental.
Oh, okay, so your question is what are the properties of the nearest black hole? And then to
Yes,
answer that
that's it.
question, you have these sub-questions. You have to figure out how to find a black hole, measure the properties.
Yes.
Okay, and the property that you measured is the spin, right?
Yes, the only one.
Okay, well, what are the, you know, what's the spin of the nearest black hole? That's fine. There must be a few more questions. Anything else? No? That's it? Okay, let's thank William again.